Problem 1. The temperature of water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes beginning at time t equals 0. Values of wt at selected times t for the first 20 minutes are given in the table above. Part A. Use the data in the table to estimate W prime of 12, show the computations that lead to your answer, and using correct units, interpret the meaning of your answer in the context of this problem. Alright, so to get W prime of 12, we're looking for a derivative or a slope, so I'm going to pick 2 points between, that 12 is between, so I'm going to get the slope of those points, so I'm going to get 67.9 minus 61.8, and it's going to be divided by 15 minus 9, and when we do that we will get 1.017, and that would be, if I'm looking for units, I had degrees Fahrenheit on the top and it was per minute. Okay, so we use the data in the table. I did show computations. Now it says to, using correct units, interpret the meaning. So what I would have for that one is the water temperature. So I'm looking for how fast that water. The water temperature is, since this is a positive number, is increasing at a rate of 1.017 degrees Fahrenheit per minute at time t equals 12 minutes. We do want to make sure we include units on that and can include units on the t value as well. So we would get 1 point for our estimate, which was just the 1.017, and then 1 point for the correct meaning with correct units. Okay, for part B, use the data in the table to evaluate the integral from 0 to 20 of w prime of t dt. Using correct units, interpret the meaning in the context of this problem. Alright, so if I'm taking the integral of a derivative, we do know that the prime and the derivative, the integral will just cancel out, and I get to evaluate it at 20 and 0, which means this is going to be w of 20 minus w of 0. If we look up the w of 20 in the table, it's going to be 71.0. W of 0 is 55. So if I subtract those two, I will get 16. Alright, so my answer is 16, and I just need to decide now what that happens. If I'm taking the integral of w prime, that's going to go from degrees per minute just to degrees, and since I got a positive 16, I know what this means. If I'm heating water in a tub, the water in the tub heated 16 degrees Fahrenheit over the first 20 minutes, or you could say from t equals 0 to 20 minutes, or whatever. So that should be that. That once again was worth 2 points. We get 1 for the correct value of 16, and we'd get 1 point for the explanation, including degrees Fahrenheit and minutes. Right, part C. For 0 to 20, the average temperature of the water in the tub is 1/20th the integral from 0 to 20 of W. Use a left Riemann sum with the 4 subintervals indicated by the data in the table to approximate 1/20th of the integral from 0 to 20 of W. So we're going to do that. And then, does the approximation underestimate or underestimate the average temperature of the water? And explain your reasoning. Okay, so 3 different things that are going on here. Okay, left Riemann sum. I do notice that we're not going by equal intervals, so I'm going to have to treat each one separately. We'll go 0 to 4, 4 to 9, 9 to 15, and 15 to 20. So for the first interval, the width of that interval is 4, and then I'll multiply it by the left, since it was a left Riemann sum, the left endpoint, which is 55.0. And then plus, the second goes from 9 to 4, so that width is 5. So we'll do 5 times the left endpoint would be 57.1. And then plus, from 9 to 15, that width is 6. So we'll do 6 times the left endpoint, which is 61.8. And then plus, the final integral, we're going to be going from 15 to 20, which is 5. So we'll have 5 times the left endpoint, which will be 67.9. Okay, and if we calculate that all out, and then don't forget, when I'm done with this, I do need to multiply by 1/20th because it said to find the 1/20th of that. I will get, and if you work this out, this is going to be 1215.8, and then times 1/20th. That will give you 60.79. And since I'm talking about an average temperature, this would be 60.79 degrees Fahrenheit. So I did the left Riemann sum. Number 2, is this an overestimate or an underestimate? And since this is a left Riemann sum and W is strictly increasing, if I were to draw my graph, I'm going to get a graph that looks something like this. So if I were to do a left Riemann sum, notice that I am leaving portions out. So this is going to be an underestimate. Underestimate, if I can underestimate. And that will be because a left Riemann sum was used with an increasing function. Okay, you could definitely, if you wanted to explain your drawing, that when your left endpoint rectangles, there's space left underneath, that is fine as well. So we got, again, 1 point for our left Riemann sum for just using it. We'd get 1 point for the correct answer, and then we'd get 1 point for saying it's an underestimate and why. Okay, for part D, for time being between 20 and 25, the function W that models the water temperature has first derivative given by W prime is equal to 0.4 square root of t cosine 0.06 t. Based on the model, what is the temperature of the water at time t equals 25? Well, since we're going from 20 to 25, and this is W prime, and I want to know the water temperature, I'm going to actually find the integral of W prime from 0 to 25. And when I do that, I do know what W prime is. So this is going to be the area, so 0 to 25 of 0.4 square root t cosine 0.06 t. And since this is a calculator, we should put dt here definitely. Since this is a calculator problem, we can use Math 9 to get that answer. And then when you get that answer, that is going to be 2.043. So that is, whoops, this is not 0 to 25, it's 20 to 25. So the 2.043 means that from time 20 to time 25, the water has heated up 2.043 degrees. But if I want to know the water at time 25, when we were at 20, my temperature was 71, so then it went up 2.043 degrees, so it is now 73.043 degrees Fahrenheit, and that was worth 2 points. 1 point for having this integral set up, and then 1 point for the right answer.